The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Good morning. So it's going to take me about 15 of the 20 minutes to go through all the participants in the project. So this was an IBRC project that began in around 2004-2005 as a part of a very small bridge construction that occurred on Anna Maria Island in a residential area. So the DOT got together with the University of Florida, submitted a proposal to replace the piles in the bridge that were going to be a standard FDOT mix with some different supplementary cementitious material additions, and then do some monitoring of those piles. So these are pretensioned, precast, pre-stressed piles that are typical of the kind of construction you might see on approach spans or in tidal areas in Florida. We worked very closely with the Department of Transportation's Corrosion Laboratory and also the physical laboratory, the concrete testing laboratory in Gainesville. In particular, I want to thank the Corrosion Laboratory and Ivan Lassa and Mario Paredes for help with making our corrosion sensors and corrosion measurement system robust. That's like fatigue testing. When you run a test, corrosion test or a fatigue test, you're testing everything that's in the load path, frames, specimen, and everything else. And the same thing with corrosion testing. If you're looking at durability, you're testing your sensing system as well as the things that you're sensing. So we did a bit of work there, and I think we've done okay. We did a 5-year check on the bridge, so I've got the timeline here. So the construction occurred around 2006, 2007. We had an initial measurement fairly soon after the bridge was opened. We did a second set of measurements about a month out, and then a third set about a year out, about when the project was finishing. And then we were invited back to do an additional measurement at about 5 years out from construction. So this was not a continuous monitoring. We had no data loggers on site. We were basically going out and doing manual measurements and visual inspection of the systems out there. So today's presentation is basically the background, the monitoring system that we installed, how that seems to be working, a little bit of data. Really, it's very boring because nothing's happening. We don't have any corrosion going on that we could detect. That's the nice kind of boring, I think. So let's get started. Our objectives, of course, with the marine environment surrounding Florida's coasts. We have a lot of bridges in saltwater. The typical construction there is to take pre-stressed, precast piles and drive them and then build a cap on top, and that's your substructure. So a very simple setup, but that does then expose the precast piles to the very high chloride levels around where the Anna Maria Island bridge is. They've tested that. It's around 20,000 parts per million, so it's very aggressive. And of course, we have very high temperatures much of the year, and that tends to move the corrosion process along. So the DOT wanted to look at supplementary cementitious materials, and we'll talk about what we actually used there. They also wanted to use this as a test bed to see how do things work short term and how do things work long term with respect to corrosion itself, corrosion of the steel within the pile. And this is, of course, is pre-stressing steel we're talking about. Also chloride contamination. So how well does the supplementary cementitious materials do with respect to penetration of chlorides? One additional kind of rider along with this, the geotechs got involved. They embedded wireless EDC sensors for monitoring the pile driving. And this is kind of a new, was a new fancy system that was more advanced than PDA, which is basically sticking an accelerometer at the top of the pile and measuring the waves as they bounce back and forth. These were installed along the length of the pile, something the DOT was looking at for future use. So not a bad place to have a project. It's on Tampa Bay or near Tampa Bay. The bridge itself, as I mentioned, is in a residential area, so it just crosses this little channel here. It's not really a navigable waterway, but we did install Fender Piles there. We talked the DOT into allowing us to do that. we're not really protecting it from anything. I mean, you're going to have fishing boats here. You can see the clearance is very low. So the fender piles were actually just sacrificial piles. So we built several extra piles and jetted those in. We didn't even drive those. The bridge piles were driven. The fender piles were jetted in, and then those are intended to be pulled later, as in years later, for autopsy, structural testing, or whatever we can think of, or they can think of down the road. The project was constructed in 2 phases, the orange and the blue there. The phase 1 was 2 sets of piles, and then the bents were divided up to accommodate the existing traffic there, and then the blue was the second phase. So the designations there, you see the CEM is all cement pile, and then we have ultrafine fly ash additions or replacements, just a straight up fly ash. And these were all, again, jetted fender piles, and then the bridge piles themselves, ultrafine fly ash, silica fume, blast furnace slag, and metakaolin. So we had a set of sacrificial piles along with, of course, we're not going to be able to pull the bridge piles. The bridge is in service. It's not something that we can mess with down the road. So the design itself is based on the standard DOT details. The piles were huge. I mean, these loads are very small. It's a precast plank bridge. Probably the biggest load's a golf cart laden with beer. So there's a golf course right nearby and residential traffic. So you're really going to have very little truck traffic. So we're not concerned with the loads there, but they wanted to look at beefy or real size piles. So they said, let's just use a 24 inch as kind of our standard size pile. So we went with that. The pile lengths, we didn't need to, there was no splicing required. So we cast the piles into 85-foot lengths for the intermediate bents and then 75-foot lengths for the end bents. And then the fender piles were a little bit shorter, easier to handle, and smaller. I went with the 18-inch standard piles there, the smallest piles that they typically produce in standard. Pre-stress level is about 1,000 psi after losses. So this followed a project or several projects with the DOT where they looked at doing physical tests and durability tests on concrete that's been made with supplementary cementitious materials. As I mentioned earlier, we have blast furnace slag, ultrafine fly ash, metakaolin, silica fume, and then fly ash was their standard. They have fly ash in all the mixes. So as you see my layout here, cement, for instance, is 100% cement. We have a total of 970 pounds per cubic yard for each of the mixtures, but we did replacement, so the FA would be minus the 20% or so fly ash that would replace cement, and then on down the line we'd have silica fume plus fly ash replacement, metakaolin, ultrafine fly ash, and then blast furnace slag. So they're really kind of ternary blends in the end when you look at it that way, because the DOT wanted to maintain that fly ash, that kind of mid-sized particle size, and then you have the finer particles in there as well. So our instrumentation, this is where we really spent a lot of time thinking about what we wanted to have in place way down the road. We created electrical connections with the pre-stressing steel, so we brazed electrical connections up at the top so that we could do potential measurements straight up on the surface of the concrete, half-cell measurements with copper sulfate electrode. We also installed isolated steel and titanium pieces that look like this using a super special process that the DOT helped us with, the Corrosion lab uses typically for their cathodic protection systems. The nice thing about this is that we can measure corrosion rates at the depth of the pre-stressing steel here because we know the area of the working electrode. And we have a nice titanium counter electrode so we can actually do straight corrosion rate measurements. We haven't done any of that yet because there's really nothing going on. All we've done is potential measurements. But we also have electrical connection with all the pre-stressing steel, and that's all tied together with the ties as well. So we have multiple ways that we can get to corrosion rates. Part of the problem with maintaining an exact height above mean high for our sensors is that the piles don't all get driven to the same elevation, right? So we actually anticipated that, believe it or not, and decided to kind of add what we called a durability segment. So what we did was, while we were casting the piles in the self-stressing form here, we subdivided a little short 4-foot section and we cast a 6-inch thick or so piece of concrete using the same concrete, same pre-stressing steel that are in the piles. And then these are actually hung from the fender piles after the bridge was constructed. So then they allow us to get the electrodes or the corrosion sensors all at the same elevation. So, with the tidal fluctuations there, then for each of the different materials, we're getting the same elevation because the corrosion rates, of course, are going to vary depending on if you're in the tidal zone or the splash zone. And so that's very important to maintain that consistency. As I mentioned, the durability segment is hung from the fender pile. So the first thing we'll pull is the durability segment at some point in time when we feel it's necessary or useful. And then the second thing that'll get pulled will be the fender pile, which is kind of sacrificial. So we were thinking, 15 years down the road, 20 years down the road, something like that. We're hoping that we don't see a whole heck of a lot before that time anyway. So as I indicated, we have corrosion sensors then installed in 3 different locations, and these durability segments were all hung at the same elevation then, so we could maintain that consistency. So the pile construction was at Durastress, so these are real piles. We were there taking samples. Lots of sampling was done, both from a durability as well as mechanical materials perspective. We had them cast us some chunks that we could take cores from. In addition to that, we did molded, both beams and cylinders, to do, like I said, long-term and short-term tests. As you might imagine, it was a bit of a coordination effort for us to make sure that when the piles were delivered to the contractor, they installed them in the place, in the orientation that we wanted them. Normally, the contractor's just grabbing the piles and throwing them into place, so we had to have the students mark the piles, make sure that we got them installed the right way up, so their sensors were in the right location, so there was a bit of a coordination effort there. Our F'(C) for the piles was 6,000, which we've got at 28 days, no problem. You can see some of the differences in the strengths there with the additions. Our monitoring program is basically, all we've done up to date is take some corrosion potentials and do some resistivity measurements between the titanium and the working electrode. We've done a bunch of laboratory tests to kind of document the concrete that was used to produce the piles. Those reports have been published and they're posted on the DOT website. We also had the opportunity to do corrosion rates down the road if so desired. So as of about 5 years out, I'll just give some real quick results here. If you look at the plot, you see the potentials versus the copper sulfate, so less than the 200 millivolts, so less negative means no corrosion. You get more negative, that means lots of corrosion. But keep in mind down here where the concrete's wet with salt water, you're going to get those high readings anyway, so what you're really looking for is kind of the movement of the upper levels, the splash zone, and the upper portion of the tidal zone kind of moving towards that more negative number as you're starting to see the potential for corrosion to occur there. The right plot shows the time, so we're 4 years out at the edge of the plot here, and we really haven't seen a change in that corrosion potential in the 4 years' time. Over the first year, you're going to see some changes because of the curing that's going on with the slower and the faster reacting materials. The DOT is very interested in surface resistivity, so we did some field measurements with that, which is a really tough test to try to get consistent in the field because the moisture content of the concrete is extremely important with that. So we did some testing with that, fairly consistent with the exception of the ultrafine flash. Not really sure why we got some elevated readings with that. As part of this work, there was some prior research done where we did bulk diffusion tests and with these ternary blends and looked at diffusion coefficients with that and the improvement in the concretes. The DOT has since, a few years ago, added this to their construction specifications, both silica fume, metakaolin, or ultrafine flash, along with the addition of flash as well for their piles. One thing I didn't mention is that they require a curing regimen in the yard. The contractor is required to leave the piles in the forms and cover them with burlap and wet cure them for 3 days, if you can believe that. So good curing process with that. Some kind of closing thoughts on structural health monitoring with respect to my experience with the project. It's been, once we got finished with the IBRC project and we finished our projects out, where does the data go? Well, it's basically stored in the report and it's online, and then I have it, and that's about it. I'm not sure how all that's going to shake out, but I think we need to start thinking about how we deal with data, how owners are going to deal with data, and I'm, of course, talking from the perspective of the bridge owner, and then data archiving as well. And how do we take care of the health monitoring system? We learned a lot of lessons in this, and we took a lot of lessons from the corrosion lab in preparing our wiring, and that actually worked very nicely, but we're only 5 years out. We're looking at 20, 30, 40 years perhaps down the road. We like to be doing in-place measurements. In place, we have sacrificial elements that we can pull out and take back to the lab. So we at least have that. We may lose the monitoring capability in the bridge piles themselves, but at least we have a set of specimens that we can look at down the road. Finally, is the health monitoring system going to outlast the subject, or is the subject going to outlast the health monitoring system? I know in my experience that the subject typically outlasts the health monitoring system, particularly when you have data loggers. When you're talking about electronics, and we don't have any of that out here, this has all been manual measurement. We considered putting a Campbell data logger out here to measure temperatures, but basically decided not to do that and just to stick with the corrosion monitoring. So thank you very much. I appreciate your attention. I'd like to point out that there are several reports on this bridge. If any of you are interested in doing life cycle modeling, there is a lot of data here that's available in the reports and would be something that you could use to test life cycle modeling or anything else. So kind of a little advertisement there. Take a picture of my email address, shoot me an email if you can't find it on the DOT website. Like I said, there's 3 or 4 reports. It's not real clear how they go together. So if you're interested in that, be happy to help you out with finding your way through there. But with that, thank you.